Hello everybody. Let us talk about block vector representation of a qubit state. Now qubits, which are building blocks of quantum computer, can be nicely represented graphically as points of the Bloch sphere. So that means all the points on the Bloch sphere represent one of the states of the quantum system. The length of the vector from the origin to the point on the Bloch sphere will be called as the Bloch vector. We want to find out the Bloch vector number 1, but we want to start from the modeling of every 2 cross 2 Hermitian matrix. Every 2 cross 2 matrix which is Hermitian in nature. Now this matrix can be expressed as a linear combination of the Pauli matrices, including the identity matrix. So there will be 4 matrices: Pauli X, Pauli Y, Pauli Z and the identity matrix, and these 4 matrices can be used to represent any 2 cross 2 Hermitian matrix as a linear combination of these Pauli matrices. Now this will form the Bloch vector representation of the qubit state. So let us try to develop the Bloch vector representation by this model, in which the 2 cross 2 Hermitian matrix will be expressed as a linear combination of the Pauli matrices, including the identity matrix. Now the basis for 2 cross 2 Hermitian matrices will be the space of 2 cross 2 Hermitian matrices is 4-dimensional. Real vector space. So that means a convenient basis is the identity matrix, the Pauli X, Pauli Y and Pauli Z. So that's the space available to represent a 2 cross 2 Hermitian matrix using these 4 entities. Now we know what is an identity matrix, we know what is a Pauli X matrix, Pauli Y and Pauli Z matrices. Now as I say, any Hermitian matrix, let us consider this matrix, let us denote this matrix as rho, which is the symbol normally used for the density operator, because we will develop the Bloch vector representation in terms of the density operator. But this is true for any 2 cross 2 Hermitian matrix. In our case, let us take the density operator as the matrix of interest. So therefore, any Hermitian matrix rho, which is the density operator, can be written as, now it can be written as a linear combination of these 4 items. So this density operator can be written as the linear combination of identity, Pauli X, Pauli Y and Pauli Z, where A0, AX, AY and AZ, these are coefficients and these belong to the real number space. So let us further proceed with this modeling of the representation of 2 cross 2 Hermitian matrices, and we apply the trace 1 condition. For density operator to be considered as the density operator, for any operator to be considered as the density matrix or density operator, it must satisfy that the trace of this density operator should be equal to 1. So what is the trace? Trace is the sum of the diagonal elements. That has to be equal to 1. So this is the trace 1 condition for any operator to be considered as the density operator. Therefore let us take the trace on both sides of equation number 1. Therefore take the trace of equation 1 on left hand side and right hand side both. So we get the trace of rho, and we take the trace of all other items, all other terms in the expression. So trace is an operation applied on this equation number 1. We know that the trace of the identity matrix is 2 and trace of all other Pauli matrices is 0. That we have already seen right at the beginning of this course. So therefore, if we substitute the values of the trace of identity and the trace of all sigmas, we will get trace of rho, because we are taking the trace on the left hand side of equation number 1 also. So trace of rho will be equal to 2a naught, because the trace of the identity matrix is 2. So therefore we get 2a naught, and all other terms will be 0. So therefore, and we say that if the operator is the density operator, the trace of rho will be equal to 1. In that case, we get the value of a naught from here, and a naught will be equal to 1/2. Let us substitute the value of a naught in equation number 1. So we get the density operator to be equal to half I, which is the identity matrix, plus ax sigma x, ay sigma y, plus az sigma z. Now we define a vector R whose components are Rx, Ry and Rz, right? So this is a vector in the three-dimensional Euclidean space. So now define a vector, rather not the Euclidean space, let us call it the Hilbert space. So this is a vector R with components Rx, Ry and Rz in the Hilbert space, and let us say that the values of Rx is 2ax, Ry is 2ay and Rz is 2az, so that we can get a reasonable expression of the density operator. In that case, we can if we substitute because R will be equal to R will be equal to 2ax plus 2ay plus 2az, right? In that case, we also define a sigma vector, which is the component whose components are the polymatrices, right? So we have two vectors now. One is R vector and the other is the sigma vector. So therefore, we apply all these expressions in this formula, which give the trace formula. And from the trace formula, we already have developed the trace, the density operator equal to 1/2 I. And if we multiply if we take 1/2 outside and we put a bracket and we take every other item in the bracket, so in that case we will get 2 with these items, 2ax sigma x, 2ay sigma y, 2az sigma z. So that is why I have taken this this R vector defined as 2ax, 2ay and 2az. So in that case, I have also defined sigma. So all in all, what is there? This term, which is basically the dot product or the inner product between R vector and the sigma vector, right? So therefore, I get the density operator to be equal to half I plus the inner product between R vector and sigma vector. R vector is the actual Bloch vector which we are interested in, and sigma vector whose components are the polymatrices. So where Rx, Ry, Rz belong to a three-dimensional real space, and it's termed as the Bloch vector. And because I have already said that rho is a density operator, so therefore it has to be Hermitian, it has to be semi-definite, and the trace of this density operator has to be equal to 1. These are some of the properties of the density operator. Now we put some constraints on the Bloch vector. So let us try to understand these constraints. For a general mixed state, now if the state of the quantum system is mixed, in that case the magnitude of this Bloch vector has to be less than equal to 1. It can be even less than 1. That means the point will not be on the surface of the Bloch sphere, because we are taking the Bloch sphere to be a unit sphere. So the length of this R vector or the magnitude of this R vector is less than or equal to 1. But for a pure state, of course, the length of the Bloch vector or the magnitude of the Bloch vector will be equal to 1. So that's another difference between the mixed state and the pure state, that the magnitude of the Bloch vector, if it is less than 1, surely it is a mixed state, but if it is equal to 1, it will be a pure state. Now the tip of the Bloch vector, so the tip of the Bloch vector lies inside the Bloch sphere or on the Bloch sphere. So that has to be understood. So if it is less than 1, so that means if it is not lying on the Bloch sphere, rather the length remains inside the Bloch sphere, that will lead to a mixed state. Now we have this expression here with in terms of the equation number 2, where the density operator is expressed in terms of identity matrix and the Pauli matrices, and we have derived this expression, this compact expression of the density operator equal to half I plus the inner product of R and sigma. Now let us put this expression of equation number 2 in terms of the matrix form. That means let us substitute the matrix form of identity sigma x, sigma y and sigma z. So let us see what we get. So once we do that, this is the identity matrix, this is Pauli x matrix, this is Pauli y and Pauli z. So we get, if we solve this, we will get the density operator in this matrix form. Now to recover each Bloch vector component, so because we want to actually do the representation using Bloch vector. So that means we must know. So what is our requirement? Our requirement is that we must know Rx, Ry and Rz. We have to calculate these values so that we can say that this is our Bloch vector. So that's why I'm saying to recover each Bloch vector component we can use. So this Ri is equal to the trace of the if we take the trace of these two operators, the density operator and the Pauli matrix, then that will be equal to the component of the Bloch vector. So I index is actually either x, y or z. So we can get from this expression, because we have the value of rho here, because we know what is density operator, we also know what is Pauli matrices, and therefore by completing this expression and by using this expression, I can get the values of Rx, Ry and Rz, which is our purpose. That means we get all the values of the Bloch vector. So mapping of qubit on the Bloch sphere. Any pure qubit ket psi which belongs to a complex world space can be written as, so any qubit can be written in this form, cos theta by 2 ket 0 plus e to the power I out of phi sin theta by 2. So this phi is the relative phase, where theta defines the polar angle and phi is the azimuthal angle. So these are basically the specifications of the Bloch sphere. And for this quantum state, the quantum state is normalized, of course, and the norm is equal to 1. That means the inner product of ket psi with itself is 1. Hence, normalization condition is satisfied. So therefore, if we now we know that what is, if it is we know from, if we have defined this, we now have ket psi, right? We know what is rho. Rho is an outer product between ket psi with itself. So we have the value of ket psi. Using this ket psi, we can find out the density operator, and the density operator will come out to be this matrix. Alright, so density operator will be equal to this matrix that I have just shown you here. Is given the elements of cos theta by 2, cos theta by 2, sin theta by 2, e to the power minus iota phi, and rest of the elements. Now we have a row here, which is the density operator. As I said, using this expression of the components of the block vector equal to trace of these two operators, the density operator and the poly matrix, I can find out each and every component. So we have now the density operator in terms of the trigonometric relations, trigonometric expressions, and we know what is the poly x matrix, poly y and poly z, and using the expression of Rx equal to trace of rho sigma x, trace of rho sigma y for Ry and R. So we can get the expression, we can get the values of Rx, Ry and Rz. So these, finally if you do the calculation, you will get the block vector as the x component will be sin theta cos phi, y component will be sin theta sin phi, and the z component will be cos theta. So this is how we will map the, so actually what we get from here, we get the block vector. That means we get a point on the block sphere. That means use starting from the if you see here, starting from the qubit state, that was the heading here, mapping qubit on block sphere. So we started with the qubit and we have mapped this qubit on the block sphere using this block vector. Thank you.